Hello, everyone. So we proceed our series of distinguished lectures of the consortium. Today, it's a great pleasure to introduce Sergei Gukov from Caltech. Sergei is a mathematical physicist who actually represents the best of both worlds. So he started his education in Russia, in Moscow, as a part of the Great Russian School in Theoretical Physics, and he continued his education in United States as a student of Edward Witten. So he's well known for his contribution to three-dimensional invariants, for Gukov-Witten buffer potential, Gukov surface Witten surface operators, and so on and so on. He has been awarded Clay Mathematical Fellowship. He is also a scientific member of the Max Planck Society in Bonn. So it's a great pleasure to introduce today Sergei, who is going to tell us about his recent progress in three manifolds.
Thank you, Ludmil, for a very kind introduction. And I want to thank Ludmil and everyone else involved in organizing this week's events for inviting me to give this series of lectures. It's a great pleasure and a privilege. So I was actually in Miami in person a couple of days ago and already miss it. So I wish I didn't have so much teaching and other administrative duties that forced me to go back. But I hope that on another occasion, I'll be able to come and see you all in person again. So what I'm going to talk about in these two lectures is very exciting developments that happen in the course of past 5 years. And I'll thank many people along the way who helped or contributed to these developments. But I guess most of all, I want to thank some of the early collaborators in this program, Dupay, Pavel Putrov, Kumarin Vafa, and Cyprian Manolescu. So all of these people, or most of them have senior positions, except maybe Dupay. So if you want to snatch him, that's a great opportunity. Since this 5 years, many papers were written on the subject, and obviously for these two lectures, I'll have to make some painful choices and try to survey certain developments, but it will force me to cut certain corners, which is quite unfortunate because one of the main messages in these lectures is going to be the interaction between different fields. In fact, as the title suggests, so I'll try to bridge topology with curve counting, with vertex algebras, and another component, which is actually a large component of this development, is mathematical physics. But unfortunately, in today's talk, for example, there'll be absolutely no physics at all, which is not to indicate that it's not represented or not to be unfair to it, since physics is reasonably well represented in the papers. I hope it's acceptable, and there will be many other painful choices I'll have to make in making this presentation. So I'll try to start with an easy definition or introduction to the subject so that we all get on the same page reasonably quickly. Namely, I'll try to explain what are we going to be discussing. So in fact, that's the main goal for today, to explain what is the object. And then mostly tomorrow, I'll explain where it comes from, what are the properties, and we'll look a little bit closer at this object. So when Brian Greene had to give a colloquium to a math department, he started in a rather formal way with the definition, of course. So in math, we want to give definitions and theorems and proofs. And he said that a conformal field theory is a table of integrals. when I had to give a series of lectures at Yale, Greg Zuckerman immediately raised his hand and pointed out that it was actually his definition of conformal field theory. And to this, I replied that it's a great definition, but I'm not sure if I fully agree with it, because it very well highlights analytical aspects of conformal field theory, but not algebraic aspects. In any case, what I think is that this definition will be perfect for our goal today. So everything I'm going to discuss in the next hour is table of integrals. So the integrals, at least the simple version of them, will be labeled by graphs. So combinatorial data of vertices and edges connecting the vertices, such that each vertex, in addition, is decorated by an integer number. So this data of vertices, edges, and numbers assigned to vertices is input. And to every such input data, we're going to associate an integral. Naturally associated with such graph is adjacency matrix of the graph, which has the size equal to number of vertices. And on the diagonal, it has the integers that we assign to the vertices. In this example, there are 9 of them, for instance. And each time 2 vertices are connected by an edge, in this adjacency matrix, we put 1 in the slot ij. So think about connectivity of a graph of friends on Facebook or some other combinatorial structure. That's going to be basically the input data for our integrals. Now, the integrals will be not quite the kind of integrals we learn in simple calculus courses. So here there will be very multiple integrals, namely there will be as many integration variables as vertices in a graph. So for instance, in my previous example on the previous page, there would be a 9-tuple integral to do. But integral actually is going to be very easy, and integrand will be assembled out of basic blocks. There will be just 2 basic rules to assign a certain part of the integrand to each vertex, namely this one, to each edge, namely this one, and then integrate the product over all such vertices and edges with theta function based on a quadratic form that we defined on the previous page. So just to pause on this for 1 second, each vertex of the graph has integer that's going to be part of the data, but it also has integration variable. So here I call it x, which will disappear, of course, in the process of integration. And each vertex integrand depends only on that particular variable. For an edge, it connects 2 vertices. So in principle, it can depend on variable xi and xj, and here denoted x1 and x2, and that's this universal basic building block that we associate to every edge in the graph. So to define the integral, I have to give you these pieces of data, namely what to associate to elements in the graph that encodes the integrand. So I define the quadratic form Q, and we take theta function for that as part of the integrand. And I also have to say in which domain we're integrating, and the rule will be very simple, that in each variable x will integrate on a unit circle. So this is, as you can see, huge table of integrals associated to various decorated graphs decorated by integers. And of course, there are as many such graphs as fish in the sea or stars in the sky. So there are plenty of examples to play with.
Are all your graphs trees or not? Because you drew trees originally.
This is just for the purpose of illustration. It doesn't have to be a tree. And I'll explain later on what it means if it's not a tree. But for simplicity, let's assume that it's a tree. And in fact, for simplicity, I'll also, at this point, going to make a simplifying assumption that on a sign of this matrix Q, the adjacency matrix, I'll assume that it's negative definite. That's again just for simplicity of our easy start with the subject. So these are the 2 assumptions. By the way, feel free to ask questions at any point throughout the talk. I want this to be a conversation, and since there aren't so many of us, we can be informal. Okay, So you can repackage the same data as I told you on the previous page. This was an easy way to remember what to associate to vertices and edges in a more succinct formula. In fact, it can be basically written as convolution of rational function with a theta function defined by the quadratic form. And the theta function is what it is, what you think it is. So here I just write the definition. One important point that I want to point out without dwelling on the details is that the determinant of this matrix will play a role, and in general, such theta function may have characteristics which take values on the quaternal of this quadratic form. So if determinant is not one, we actually have several, not just one theta function. And this label B, which labels different choices of theta function, will play a role. So in the end, what did we get? We get the integral over many, many variables, as many as vertices in a graph, which depends on quadratic form, depends on these additional choices for theta functions. And it depends on variable q, which enters the definition of theta function. And it also was entering slightly part of the integrand for vertices via this term. So variables x get integrated out, but variable q remains there. And this discrete data of choice of a graph for labels b also remains part of the final answer. So therefore, to each graph, we associate lots of such integrals. What's interesting is that the result that we get enjoys certain symmetries, certain invariances, which takes us from a simple problem in, you could say, calculus, because we're doing basic integrals and they can be easily done by residues. So that's not far from calculus, to Kirby calculus. Namely, each integral I showed you actually depends on the graph. You could ask, is it how much dependence on the graph is there? And one possibility could be that for every graph, the answer is always 1 or 0, for instance. Well, this doesn't quite happen. So the answer turns out to be non-trivial function of Q, in fact, Q series, and its properties I'll state later on. But it's not that it's a different answer for each different graph. Namely, some graphs gives you the same answer. And these are exactly the equivalence relations that you can find in a textbook on low-dimensional topology, such as this textbook on Kirby calculus by Gomov and Stipschitz, and in many other places. And the operations on the graph are usually called Kirby-Neumann moves. Here are some of the main examples. Namely, you can actually change number of vertices in the graph, which means that we're changing the number of integration variables and the size of the adjacency matrix changes. But the result of integration remains the same if changes are made according to this very particular rule. So that you take a vertex labeled by A and you append to it another edge and another vertex, or you can do this in the middle of the graph between some two other vertices. And there are a couple of other rules that are very simple. These are basically analogs of Rademeister moves for 3 manifolds constructed in such way from this graphs, and represent equivalences in ways of building same 3 manifold via different procedure. I'll say more about this procedure later, but at this point, what we learn is that these integrals that I defined for you are actually invariant under this Kirby-Neumann moves, and therefore, by definition, we essentially check that these are invariants of 3 manifolds. So even though the problem started as table of integrals, the way Greg Zuckerman or Brian Green would put it, it ended up being invariant under this Kirby-Neumann moves. And this means that this table of integrals represents certain invariants of 3 manifolds. So that's basically the beginning of the story, which one can formalize in this theorem, which goes back to this work with Dupay, Pavel Putrov, and Kumran Vafa. And various elements of this theorem were improved in further papers that we wrote with Ciprian, as well as nice work by Catherine Brinkman, Carl Marlbrook, and Anton Milish. In particular, where this assumption on Q being negative definite was relaxed to much weaker open condition. It's also of the inequality type, but much weaker inequality. So what this theorem states is the following. These are some of the basic properties of this invariance. So first of all, it's easy to show that all these integrals converge inside the unit disk. So when Q is strictly less than 1 in absolute value, but not equal to 1, not in the boundary, then all these integrals are perfectly convergent, and this you can do by easy ratio type test. Also, we saw that it depends on characteristics of the theta functions, which are in the quaternal of this quadratic form. And since now we know that to such a graph, we should associate a three-manifold, this quaternal actually has a meaning in topology. It's exactly first homology of the three-manifold associated to the graph, or as a set, it's also the set of spin C structures on a three-manifold. So depending whether you prefer spin C structures or first homology, you can think of this elements B as living either here or here. Spin C is a slightly better choice, and as I'll try to explain later in the talk, that's the right way to think about it. But if you're uncomfortable with spin C structures, think about elements in H1. It's not a big mistake, at least for many things I'll try to say, or at least it's a good approximation.
So this is rational homology sphere. H1 is finite, yeah?
Not necessarily. Yes.
Because
so
you said says Q is negative. When it's negative, then it should be non-degenerate, I suppose. Yeah.
That's right. So, but as I promised, we're going to relax some of these assumptions. In particular, we're going to relax the condition on it to be definite. So determinant may actually even vanish. So then we'll have first Betti number. It will be infinite, and we'll allow loops in the graphs that will have the same effect as introducing the Betti number, first Betti number. So it doesn't have to be finite. And in fact, even in this talk, and more so tomorrow, I'll show lots of examples with H1 infinite. So we'll slowly move from simple things to more advanced things. Yes. So another important property of, at least in the context I showed you so far of these integrals, is that they have integer coefficients, and that's going to be important for a reason I'll say later. It means that these integer coefficients are counting something, and the counting aspect will be in tomorrow's talk. But at first today, I just state this as part of the theorem that it's not too hard, but it requires some work to show that in all of these cases, the coefficients are integer, and so are powers of Q, except for overall leading power, which I call delta. For different choice of B, it may be different. And this power will actually have a topological meaning as well that I'll explain by the end of the talk. Well, I already showed that it's invariant under Kirby-Neumann moves. And next natural question, if this is really an invariant of three manifolds valued in Q series defined inside the unit disk, natural question, have we seen this invariant before? So unfortunately or fortunately, the answer is no. So it's a completely new gadget. But if you take radial limits when Q goes to roots of unity, it gets related to many other familiar invariants, in particular the ones you can construct from quantum groups. And later in the talk, I'll give you a map of different relations to different invariants. Okay. So once we meet some new object, of course, it's natural to have a lot of questions. First of all, where is it coming from? For instance, this integral that I showed you, what's the origin of it? Clearly, various parts of the integrand were chosen carefully so that the result is invariant under this Kirby moves. If I made a slight mistake, it wouldn't be invariant under Kirby moves. So what's the motivation, and where did it come from? what are the properties? All of these are valid questions, and I'll try to address as many of them in this limited time of 2 lectures as I can. So again, I had to make various painful choices. I'll try to tell you about different aspects of the result. And one of my goals will be to illustrate once again that it sits at the crossroads of many different fields, including curve counting, vertex algebras. And today, most of my focus will be on topology, and I'll tell you a little bit about quantum group origin or nature of this invariant that I just introduced in some class of examples. Leaving most of the motivation and goals for tomorrow, I want to mention just one motivation that was important for us in this work at early stages. And this has to do with the so-called categorification program, which has been extremely successful at the level of knots. And it basically represents integer coefficients of famous knot invariants, such as John's polynomial, as graded Euler characteristics of homology groups. In the case of John's polynomial, that would be Hovanov homology. So it's natural to wonder, given the close relation between knots and 3 manifolds, that analogous categorification should be possible for 3 manifold invariants, which in the case of, for example, SL2 at roots of unity would be Witten-Reshetikhin Turaev invariants. So it's natural to ask whether at kth root of unity, WRT invariant of a 3 manifold can be similarly written as sum of dimensions of cohomology assigned to the 3 manifold. So this is a very natural question, and many people ask this question. In fact, even before Hovanov homology was invented, there was a wonderful work of Crane and Frankel, which basically paved the way or direction in which this should go. But unlike the case of knots, for 3 manifolds, one immediately faces an obvious challenge that if you compute, say, WRT invariants at kth root of unity for a simple class of 3 manifolds, which is shown here, you see very explicitly that it's not really a function of Q with integer coefficients. First of all, it's function of K, which is the order of the root of unity, and K appears in all kinds of places. Appearance on the sign is not so bad. You can write this in terms of Q, which is exponential of 2 pi I over K. But K, which is roughly log of Q, appears as upper limit of the sum. It also appears here as a prefactor in some random power. So this is clearly not something obvious in terms of Q at all. And this has been a challenge for one of the main issues with categorifying 3 manifold invariants based on quantum groups. Most of what I'll do today will be for SL2, but generalization to other Cartan types is known. And various people, various groups approach this challenge in different ways. So one based on mix of Hopf algebras and homological algebras, affectionately called hopfological algebra, was introduced by Misha Hovanov and pursued by Anna and others. Raphael Rucker and his colleagues use high representation theory. And today in this talk, I'll try to approach this challenge by finding a function inside the unit disk, which extends these values of WRT at roots of unity inside the unit disk. So that function of Q in the unit disk will have integer coefficients, and that will have nice categorification properties or potential for being categorified. In fact, that's exactly this sort of integral. That's its purpose in life for the sake of this particular motivation. It's a shadow, namely graded Euler characteristic of a doubly graded homology group assigned to a manifold and a choice of this label B, such that its graded Euler characteristic is precisely this Q series Z hat that I introduced for you early on in this talk. So I won't say anything in this lecture about homology. I just want to mention that this is main motivation, at least for many of us in developing this. But these lectures will be entirely about simpler object, namely this Q series itself, because even in this case, there will be a lot of work needed. And
sorry, Sergei. Yes, it was this talk on actually on this series by Don Zagier about his, I think it's appeared by Don and Grofalidis. They also have this series related to something here too, I think to manifold and SL2. Is it the same? Because I
No,
think it's kind of almost, yeah, I don't know.
I think that's a great question. Yes, I always encourage to use this to explore the relation between the two. But as far as I know, these are not the same. So they have some.
For example, the Q series satisfies some Q difference equation. You use as well.
Yeah, the same is going to be true here. So many elements are extremely similar. That's why I personally think that they should be related. In fact, I think that's that they're close enough to be related. My understanding from their papers just starting to appear, that they seem to say there is no direct relation, but I think everybody expects that they should be related. That's a great question. I think we should ask them actually to comment on this. Yes. Right. So to us, big surprise was that in trying to continue this WRT invariance inside the unit disk, you get not a single Q series, but several of them labeled by this label B, which is element of H1 of the 3 manifold, or as later was recognized by spin C structures. And in fact, this is one of the reasons why I think at this point it's not clear how it's related to work of Stavros and Don, because in their work, I don't think spin C structures appeared. But again, since they're working on it, maybe they will find it soon. I'll try to explain in this talk that spin C structures are extremely natural and very useful for this construction. But I should point out that to me, in the very beginning, this was a big surprise 5 years ago. In fact, when we first came to this conclusion with Pavel and Kumran, at first I almost refused to agree to this conclusion. It seemed to me that this is too silly, in particular because back then, identification of these labels with H1 or equivalently with a billion flat connections on a 3 manifold didn't seem to play well with my affection to hyperbolic structures, which are non-abelian complex flat connections that seem to play an important role in previous developments. And we had to make a trip to Santa Barbara, where Kumran Vafa was visiting at the time with Pavel, to spend the entire day, and they convinced me that this should be true. So I'll try to share with you part of this conviction. So I certainly believe that this is correct label set for this Q series. And later on, a couple of years later with Cyprian, and then in work with Hirako Nakajima and various other collaborators, we found that a better way to think about this label set as spin C structures on a 3 manifold. Again, these are two isomorphic sets, but not canonically. And this in a way is even more surprising because spin C structure is a lift of spin structure on a 3 manifold, and WRT invariants certainly don't require any additional structure. They don't depend on spin structure. So therefore, the only hope to recover WRT invariants at roots of unity, which I presented to you as a motivation, is not only take the radial limit, Q goes to root of unity, but also sum over spin C structures with some universal coefficients. And this is indeed what happens. But then this opens basically another set of questions. For instance, what happens if we don't sum over spin C structures? What kind of invariants are this Q series, and are they related to other invariants labeled by spin C structures? So these are the kind of questions that we'll discuss today. And just to illustrate, for instance, if you have some so-called small surgery on a knot, then you should expect one Q series. There is only one spin C structure. If you have integer surgery, you get as many as a surgery coefficient. And if you have examples such as S1 cross S2 or S1 cross a Riemann surface, you would have infinitely many spin C structures. So this is a little crazy, but you'll have infinitely many Q-series in these cases. And I'll show you actually examples of this in a second. So today I'll focus on construction of this Q-series invariance labeled by spin-C structure, because before we discuss their properties, which is what will come tomorrow, and I'll say more words about motivation, we have to know what is the object, namely what are we dealing with. So that's the main goal for today. So there could be many ways to construct this invariance based on different ways of constructing three manifolds themselves. For example, Higger decomposition or other techniques. Some of them need to be developed. The only one which has been developed pretty far is based on surgeries. And actually that's the one I secretly used in the beginning of this talk for slow introduction. According to a theorem of Licorice and Wallace, every closed three manifold can be obtained by integral surgery on some knot or link. So here we color the components of the link by integer surgery coefficients. And from this point of view, for example, 3 torus, a familiar three manifold, is not just a Cartesian product of three circles, but rather surgery on a Borromean link or some other link with surgery coefficient 0, 0, 0. So that's a surgery presentation of a three manifold. And in the surgery presentation, main ingredient, or in this approach, main ingredient is to associate the Z-hat invariance to complement over a knot or a link. A knot complement has infinite H1, so H1 is equal to Z, and it has infinitely many spin-C structures. So it's convenient to organize, package all of these Z-hats Q-series for knot complement in a formal generating series introducing this variable X. So if you have a link with many components, there will be many X's. And in fact, you should start seeing connection to what we discussed before, because essentially the plumbing graphs that I showed you earlier represent links made out of unknots. And if that's the case, then indeed, for each component of this link made out of unknowns, you have integration variable xi that we saw before. And if you want to replace now one of the unknowns by some more interesting knot, what's going to change is part of the integrand is going to change in this definition. So I have to tell you what to do if you, in our previous discussion, replace one of the unknots by more interesting knot, or in general, if you replace it by a link. So this was precisely the goal of our work with Cipri and Manolescu. And we proposed, basically in that work, we tried to study two ways of extracting this Q-series for knot complement. So we call it two variable series because it has variable Q, same as before, and it has variable X, which encodes dependence on the spin-C structure. So one approach was based on recursion relation, which says that quantum A polynomial annihilates this function. This is very similar to what Maxime mentioned a moment ago. And in my opinion, this is good potential for collaboration and developing these fields together. Another approach was based on resurgent analysis, which focused on very well-developed techniques for computing certain partition functions or invariants near Q equals 1 as a formal power series in H bar, and resumming them in a power series in Q, which means that we transfer the main for this function from neighborhood of Q equals 1 to Q equals 0, because when we write something as a Q series, we of course mean that next term in the Q expansion is smaller than the previous one. So this is naturally expanded near Q equals 0. So each of these deserve perhaps a separate talk on its own. I'm just, again, this is more like a survey, so I'll say a few words about these techniques, and especially the second one, this resurgent analysis, which is extremely popular these days. And Maxime, for example, has many nice lectures on exponential integrals, explaining techniques that allow us to go from such so-called perturbative series to Q series, for example. So all of these techniques, both this recursion relation and resurgent analysis, require some work, but they also require certain initial conditions. For instance, if you want to solve this recursion relation, then question is, I mean, this operator, Q difference operator, is extremely concrete, but you have to start with some initial condition for this function, for this double series. So this is something that I'll try to illustrate for you in real time. And initial condition that we used with Chypre and Manolescu is a property that as Q goes to 1, this two variable series becomes inverse Alexander polynomial of a knot. And this is something fairly simple. So Alexander polynomial, introduced by James Alexander II and almost a century ago, can be defined by skein relations. So if you have a knot diagram, you can use Alexander polynomial of a knot equal 1 as initial condition, and then the usual rule for changing the types of crossing to compute it for every simple knot. So for instance, for knots such as trefoil, figure 8, 5, 2, these are simple examples. And by now, Alexander polynomial has many, many definitions. I think I know about a dozen of them. So it's related to many aspects of knots and in knot theory. And it can be also defined as enumerative invariant, for example, thanks to work of Novikov and more recently Mike Hutchins. You can express Alexander polynomial as counting periodic geodesics for a periodic Morse function on a 3-manifold. And in that approach, you have to fix a homology class where a periodic geodesic is going to live. And this naturally is a class in first homology, H1, which also relates well with the fact that X, this variable X that we introduced, has to do with the first homology of the 3-manifold. Anyway, coming back to our goal, how to construct this two-variable series out of inverse Alexander polynomial. So let me take one example. I'll take, for example, figure 8 as something concrete and do for you an experiment in real time. So every time I do this, I get a little bit scared because this is almost like trying to do a magic trick in real time, but let's see if it works. So I'll try to open Mathematica file and expand. So let's see. Write the inverse Alexander polynomial for the figure 8 knot. So let's see if I remember this correctly. That's, I believe, what appeared on the slide in the table for Alexander polynomials of simple knots. So I'm typing that expression, and important part is denominator, which is Alexander polynomial of the figure 8. So I'll expand that, for example, in X up to order 20. So I hope I didn't make a mistake. So let's think, let's look at the coefficients. Of course, it's a rational function, so powers of X go all the way to infinity, but powers 1, 3, 5, and 7, for example, have coefficients 1, 2, 5, 13, 34, 89. Okay. So I'll stop sharing this part. I'll go back to my slides. And so yes, that's the Alexander polynomial of the figure 8. So I put this at x squared in my experiment. And these are the coefficients which we just saw a moment ago. Power 1, 3, 5, 7 had coefficients 1, 2, 5, 13 in the Mathematica notebook. So what happens is this Z hat labeled by spin C structures in spin C structures 1, 3, 5, 7 basically become function of Q such that as Q goes to 1, it reproduces our constant coefficients. So that's the good initial condition that can be used for either recursion relation or resurgent analysis, either of these two tools that we used with Cyprian to recover Z hat from inverse Alexander polynomial. And I just tried to show you that it's extremely easy. It's fairly concrete and simple. So you can use these values at q equals 1 as initial conditions, and then using either q difference equation or resurgent analysis, reconstruct the q dependence. So that's what we did. And here you see that indeed, if you set q equals to 1, going backwards, for instance, from here you get indeed 5, here you get 13. It's a little harder to see that summing all of these coefficients, you get 34, and so on and so forth. So I encourage you to play with this yourself. It's a lot of fun with this Alexander polynomial game. And then the reason we need this is, again, as a fuel for the surgery formula. So remember, we're constructing three-manifold invariants via surgery operation. So this becomes part of the integrand that depends on variable x. We stick it in the same kind of integral. Today is all about table of integrals, and integrate over variable x with suitable basically same type of formula that I showed you before, and variable x disappears, but as a result you get invariant of a closed three-manifold, which is a surgery on a given knot or a link and so on. So here, if I compute for you this recursively double series for figure-8 knot, then I can feed it into the surgery formula, and you get a Q series, for example, for minus half surgery on figure-8, which is one of the simplest hyperbolic surgeries. So then this was back in 2019, 2 years ago. And it was a very interesting time or situation where we could compute this Q series to arbitrary accuracy based on this either recursion procedure or resurgence. You find the coefficients are growing in absolute value. They're all integer. That's exactly what we wanted for categorification purposes. They're oscillating in sign. So this is a plot of coefficients. You see that absolute value grows pretty quickly. It's 15,000 for q to the 500 and so on. The sign is changing, so they're not just positive and negative. That's of course very typical for being graded Euler characteristics of homology groups. But we couldn't recognize what this function is. And back then, 2 years ago, I think, when I started giving talks and including, say, one at the IHS and many other places, I think I offered a bottle of wine to anyone who could figure out what this function is. So one can provide thousands of coefficients, but can we write it in a closed form? Or can we recognize, is it a Q hypergeometric function? Or what is it? And of course, you get this answer for many non-trivial knots and many surgery coefficients. So this was a little bit puzzling or frustrating. And various people got back to me with some partial feedback and thoughts, but until basically a few months ago, it was not recognized what this series is. And then tomorrow I'll tell you the answer. It's actually something surprisingly nice and beautiful, but
but does it satisfy Q difference equation?
This one by itself does not, because
does not. I see.
Yeah, what satisfies Q difference equation is this series that has both X and Q. So X keeps track of spin C structures on a knot complement, and so yeah, tomorrow maybe I'll say a little bit more about it from a enumerative perspective. That's going to be quite familiar to Maxime from the viewpoint of quantum curves that appear in enumerative geometry. So that's going to be exactly the same type of quantum curves, and quivers will come in and other things. But this, of course, is meaningful when we have variable x, because then we can write y as a shift operator, x as multiplication operator. They form the Weil algebra and or quantum torus, and we get the usual story of this quantum A polynomial annihilating this function. But once we perform a surgery, we only get an answer which depends on Q. So Q is still inside the unit disk, and that's what this game is all about. But variable X is basically replaced by a choice of spin C structure. And previously, there were infinitely many spin C structures on a knot complement. That's why we had variable X in the first place. That's the role it plays in the Alexander polynomial. But after surgery, it depends how many spin C structures we decide to keep. So if we do, say, some finite surgery, then out of X, only finitely many options remain. In this case, basically none, because this is integral homology sphere.
Sorry, so it was a stupid question because we have no variables to make two different equations. Yeah.
But it's a good question. There is no such thing
Yeah,
as a
but
stupid
it's
question.
I suppose kind of like period of equation depending on Q. Yeah. Anyhow, yeah.
Exactly.
Yeah.
Right, so tomorrow I'll reveal the answer what this is in a closed form. And of course, not just in this example, the goal will be to explain the general structure, but let's proceed with the definition or construction of this object. I told you what we were doing with Cyprian a few years after this original work with Pei, Putrov, and Vafa. And we had two methods, namely recursion and resurgence, and it all looks beautiful. But we actually managed to work out only one more example, one new example compared to what was known before, namely this figure 8 knot that I showed you. And in this table of knots with up to 7 crossings, still many remain as question marks. So we were a little bit frustrated because all this is nice work and in principle reasonably systematic, but it requires a non-trivial amount of effort. And we basically couldn't easily get the answer for even the next hyperbolic knot 5-2 or 6-2, 6-3 or 7-7. So it wasn't clear whether having these two methods were fantastic, but and I encourage younger members of the audience to try to push them for, say, 5-2 or 6-2. They should definitely be doable. But it was clear that if we really want to be useful for topology and develop this invariance in a way that they're really computable, and I want to emphasize easily computable, then this may be not quite the way to go. So this was the status in 2019. And luckily, just a year later in 2020, and in fact, more recently in 2021, a student of mine, Sang-Yuk Park, came up with a very clever method to compute this double variable series for knot complements and possibly more generally for link complements using our matrix technology for quantum groups at generic Q, which is basically mimicking Rishitihin-Turaev construction. It's a little delicate. It's using infinite dimensional modules called Verma modules, unlike the finite dimensional ones for Rishitihin-Turaev construction. And that's, of course, natural because he's working a generic Q. But basically, it knocked down all of the question marks in here. So now we know very explicit form of this series for knot complements, pretty much for every knot up to 10 crossings, for many infinite families, such as homogeneous knots, double twist knots, positive braid knots, and so on and so forth. So for instance, for 10 crossing knot, now there is no problem to compute its surgery and then produce this multiple set of Q series. So it's extremely computable, and definitely this R matrix technique so far remains one of the best for computational purposes. Works like a breeze. I want to give you another definition of this invariance, which is not as computable as what I just said, but it's conceptually maybe useful, and then it's somewhat computable. So we're constructing invariance of 3 manifolds, and this Z hat is obviously a TQ of T, which depends on choice of spin structure or spin C structure. And in general, as Ati told us, there are useful rules, algebraic structures that accompany cutting and gluing procedures. And in 3-dimensional TQFT, there are 2 vector spaces that one associates to a 2-sphere and a 2-torus, namely genus 0 and genus 1, surface that play a very special role. Genus 1 has to do with Grothendieck group of tensor category that if TQFT is extended, gets associated to a circle. That's of course very special, and that plays a very important role in work of Rishitihin, Turaev, and follow-ups. But I want to focus on vector space that one associates to a two-sphere. This is in general commutative ring because there is an obvious map analogous to pair of pens. Think about Swiss cheese, or maybe that's a good place to think about Swiss cheese operades, if you like operatic language, where inside a big three-dimensional bowl, I remove two smaller balls, three-dimensional balls. Therefore, we get a map from two spheres to one two-sphere, and that's precisely the product map. This gives this structure of a ring. And as it's commutative, it's a good question to ask, what's the spectrum of this ring? So that's going to be some variety. I'll call it M. In recent work of Braverman, Finkelberg, and Nakajima, there was a mathematical definition given to so-called Coulomb branch, and that's actually a good example to think about. And my point is that whenever you have a three-dimensional TQFT, it's a good idea to ask what is invariant for a two-sphere or S1 cross S2. This is supposed to be basically Hilbert series of this space. So let's ask what is it for the Z hat TQFT? Well, the invariant for S1 cross S2, again, this has infinitely many spin C structures. That's why variable X appears all over, for same reasons as before. So this was computed back in our original work with Pei, Putrov, and Waffe, and this is the answer. So it's some ratio of Kuperheimer symbols. They also depend on variable T besides X and Q that are familiar to us, and this T has to do with refinement or categorification. I'm not going to say much about it today. In any case, motivated by the previous slide, let's ask, is it a Hilbert series of something? Is it a Hilbert series of any space? Well, this is a very infinite series, obviously. And as such, of course, it can be a Hilbert series of something only infinite dimensional. And there is actually a beautiful space, namely roughly cotangent bundle to affine Grassmannian that has for SL2, so the group here is SL2 or SU2, for which this is indeed a Hilbert series. So this brings me to another definition of this invariance, which can be computable, at least for fairly simple manifolds. Namely, the Z hat can be defined as a Rosansky-Witten TQFT whose target is cotangent bundle to affine Grassmannian. So in this definition, it's clear that it depends on spin C structures, namely this variable X that we saw all along indeed is a variable associated to spin C structure. And luckily, mathematical definition of Rosansky-Witten theory is known, in fact, using slightly different techniques, either formal geometry or T classes, thanks to Misha Kapranov and Maxim Kontsevich. So that's yet another definition you can try to work with. Okay, so in the remaining 10 minutes, I want to explore this. So once we have a way to compute this for manifolds with boundary, we have a gluing operation, namely the surgery formula, and can compute it for many closed three manifolds using surgery technique. We should slowly transition into asking about the properties and connections to other fields. So now in the remaining 10 minutes, I'll try to explain the first part of the title to this lecture series and uncover the topological meaning of these invariants, namely ask how they could be useful for topology. And to do that, we'll compare this new invariant, which is, of course, depends on the three manifold, depends on the choice of spin C structure and variable Q, to other invariants of three manifolds that depend on similar data, namely choice of either spin or spin C structure. So to start with, we'll go back to early 50s and the work of René Thom and Lev Pantragin, where they introduced the notion of equivalence classes on manifolds by saying that two manifolds of a given dimension belong to the same equivalence class if they can be realized as boundaries of manifold of one dimension higher, becomes a boardism or co-boardism between two that we wish to put in the same equivalence class. Depending on which additional structure we impose, such as orientation, spin structure, and framing, and many other choices, one gets different types of the so-called boardism groups in different dimension. And here is a table illustrating these boardism groups for manifolds equipped, d-dimensional manifolds equipped with spin structure. Since we're talking about three manifolds, our attention should probably go to this slot on the table, where fortunately or unfortunately, this spin boardism group turns out to be trivial. So it seems like we are out of luck, but not quite. In 1952, Vladimir Rokhlin used exactly this fact that spin boardism group in dimension 3 is trivial to introduce Rokhlin Invariant, as we now call it, basically by saying that since every three manifold can be bounded, it can be realized as a boundary of a four manifold, we can use Rochlin's theorem for closed form manifolds, which says that signature of a spin closed form manifold is divisible by 16, to define a defect, an invariant of a three manifold equipped with a choice of spin structure. And that's going to be basically signature of the four manifold mod 16. So this gives us a mod 16 invariant called Rokhlin invariant of a three manifold. Important point, it depends on the choice of spin structure. Very much like that hat that depends, requires the choice of spin structure. Another version of cobordism group is a so-called homology cobordism group, usually denoted as theta3z, z to emphasize that it's based on integral homology spheres. Namely, this is a version where you require all manifolds participating in this construction to be homology spheres. And the cobordism itself should be homology cylinder. So should have homology of, in our case, F3 cross an interval. In this case, when we talk about this homology three spheres and the corresponding cobordism group, it's actually not known what the group is. So this is one of the cool problems in low dimensional topology, where we actually don't know what the answer is. So thanks to Rokhlin and Rokhlin invariant that I showed you a moment ago, you can show that this group is non-trivial. In fact, Poincare sphere has non-trivial Rokhlin invariant. The work of Fintushel and Stern told us that it contains Z as a subgroup, and then later on Froishov, using gauge theory techniques, showed that it contains Z as a summand. So we also know that it contains Z infinity as a subgroup. I think now we also know that it contains Z infinity as a summand, though I may be mistaken. And a lot of insight into the structure of this group and invariants that distinguish different boardism classes in this group in recent years comes from work of Osvald and Szabo and Higard-Fleur homology under the name of correction terms. So these are also invariants of three manifolds that depend on choice of spin C structure, or again, if you prefer, think about elements in H1. And they are constructed using homological invariants, very much like motivation that was main motivation for constructing this Z-hat invariant. And by now, there are several formulations of Higard-Fleur homology, either in terms of Cyberquit and monopole equations. This was developed by Konheimer and Mrówka and goes by the name of monopole Fleur homology. It's a theory which has four different variants, and these four variants match definition based on symplectic or rather contact geometry developed by work of Taubes and in a follow-up by Mike Hutchins in the way that I already mentioned earlier. That's called embedded contact homology. And there is yet another combinatorial / symplectic construction due to Osvald and Szabo. That's what we call Higard-Fleur homology. And again, it comes in four flavors, such that across the board, these four flavors of homology agree. And one of the flavors can be used to define this rather delicate rational invariant of three manifolds equipped with spin C structure called correction terms. These correction terms are quite important because they quickly gave new proofs of Donaldson diagonalization theorem and Thom conjecture. And here is an example of what these correction terms look like, for instance, for length spaces, just to be concrete. So now I can put this together on a map and summarize how this z-hat invariant, which is also labeled by spin C structures and defined in the unit inside the unit disk, relates to some of these other invariants. For instance, correction terms are related to fractional powers of Q, the overall powers that we saw earlier, and that's the behavior of this z-hat near Q equals 0. If you take a radial limit, Q goes to I, and not sum over spin C structures, but keep the dependence on spin structure, you actually recover Rokhlin invariant. So z-hat and its dependence on spin structure is non-trivial and recovers Rokhlin invariant of the 3 manifold. I talked a little bit about Turaev torsion in our discussion of Alexander polynomial, because Alexander polynomial is basically Turaev torsion for knot complements. So the statement, which is general and works not only for knot or link complements, but closed manifolds, is that if you take a limit Q goes to 1, you recover inverse Turaev torsion in exactly the same way we saw very explicitly inverse Alexander polynomial recovered from this 2-variable series for knot complements. And again, spin C structure is kept intact. We're not summing over it. And finally, something I didn't really talk about, but you can try to do is if you sum over spin C structure, you can recover some of the known invariants at roots of unity, such as Gutsu-Deguchi-Otsky invariant, Constantina-Gir-Potero, Miranda invariant, or Witten-Reshetikhin-Turaev invariant, and various others, which may depend on additional structures, but not quite spin or spin C structures. So that's the big map of various other invariants in topology, and hopefully it explains half of the title of these lectures, how complex plane, or rather the unit disk, can be used as interpolation between, say, correction terms, Rokhlin invariant, or Turaev torsion via this Q-series invariants, which are defined inside the unit disk. And tomorrow we'll talk more about enumerative interpretation of these integer coefficients, which was important to us. So I think I'm running out of time, but I wanted to briefly mention in the end yet another work of Ahmed Johnson and Slava Krushkal, where they also build on this connection to Higard-Fleury homology that I mentioned earlier. In particular, there is so-called lattice cohomology introduced by Andrzej Nemeti, that's also invariant labeled by spin C structures, invariant of 3 manifolds. And using this setup, they define the double hat, some invariant which in the limit T goes to 1 reproduces what I told you about in this hour. But since I'm out of time, I probably should skip this part, and thank you for your attention.
Thank you very much, Sergei. Any questions?
Yeah, sorry, I have a question again to Maxim. This in all your stories was secretly about SL2, yeah? This kind of hidden parameter. And if there is other Dynkin diagram, what will replace spin C structures? You get many copies, like rank of the group, or what?
That's exactly right. Yeah. So first, I should mention that this is unfortunately one of these painful corners I had to cut. Especially, I feel bad about it because this part was developed by younger people, Hee-Jung Chung, Sanyuk Park, and more recently, my current student, Angus Gruen. So they generalized many of these constructions, including this quick and effective R matrix techniques to Cartan types other than A1. And what happens is that in the surgery formulae, we basically get integrals over Cartan of the group. So the reason we had one-dimensional integrals in many of these examples is because Cartan of SL2 is one-dimensional. In general, for each vertex or each node, you'll have as many as rank of the group integrations. And you're absolutely right that in terms of spin C structures, there will be multiple copies of spin C structures. So it will be basically, for instance, for Cartan type AN, symmetric product of spin C of the manifold. This is going to be the labels.
Okay, thank you.
Other questions? So if not, let's thank Sergei again. And so we proceed tomorrow at the same time with the second lecture. Thank you very much.